What's going on, guys? Welcome back to a new one today. Before I get into this one, I want to say if you're looking for an internship or job, check out the top link in the description. It's a newsletter that I post. I've been trying to be more active on it, but to really teach you how to land a internship or job. So check it out. But with that being said, today we're going to be continuing the part two of our hash maps series here. So we're going to be learning about collisions. So remember, hash functions are designed to compress data from a large number of possible keys to a much smaller range. Because of this compression, it's likely that our hash function might produce the same uh, hash value for two different keys. So it's known as a hash collision. Now, there are several strategies for resolving hash collisions. The first strategy we're going to learn about is called separate chaining. The separate chaining avoids this by updating the underlying data structure. So instead of it being like an array, it's going to be a data or a linked list. So basically, let's say you have a hash map, um, and you're mapping both garlic and onion to the two, right? To index two. Now, if you have both of these in the same index, you're gonna have a collision. So what happens is you can chain it, meaning, okay, let's put garlic in, and then right next to it, garlic will point to onion. So this will hold like a linked list. If you watched the previous videos, you know a linked list is one node pointing to the other, and it just creates that chain. That's why it's called separate chaining. And separate chaining is like this. So a hash map with a linked list separate chaining strategy follows a similar flow to hash maps that have been described so far. The user wants to assign a value to a key in the map. The hash map takes the key and transforms it into a hash code. The hash code then converts that to an index to an array using the modulus operation. If the value of the array at the hash functions returned index is empty, a new linked list is created with the value as the first element of the linked list. If a linked list already exists at that address, append the value to the linked list given. Basically, all this means is if you have like a hash function and both of these, let me see, we'll do key, we'll keep the key the same, value we'll do Bob. You see how if we add it to the same key, like right here, we'll do one and we'll do SpongeBob. I guess SpongeBob. Okay, you guys get it. So SpongeBob will be added in number 4. Now let's say we also add in Patrick. And the same thing, okay? See right here, you guys will get a link list structure. Now let's put this as 2 and let's add in Sandy. Now it's gonna be the other key, and Sandy's gonna go here in the hash function. So that's basically separate chaining. It just keeps creating like a linked list structure if you have multiple values that go in the same index. That's all that is. And then saving keys. So a hash collision resolution strategy like separate chaining involves assigning 2 keys with the same hash to different parts of the underlying data structure. How do we know which values relate back to which keys? If the linked list at the array index given by the hash has multiple elements, they would be indistinguishable to someone who with just the key, because again, they're gonna be under the same index, so these values here will be corresponding to that key. Now, if we say both the key and the value, then we'll be able to check against the save key when we're accessing the data in a hash map. By saving the key with the value, we can avoid situations in which two keys have the same hash code where we might not be able to distinguish which value goes with a given key. Now, when we go to read or write a value for a key, we do the following. Calculate the hash for the key, find the appropriate index for the hash, and then begin iterating our linked list. For each element, if the saved key is the same as our key, then return the value, otherwise continue iterating. So we have open, addressing, linear probing. Now, linear probing is another type of hash collision strategy, and it's called open addressing as well. Now, in open addressing, we stick to the array as our underlying data structure, but we continue to look for a new index to save our data if the first result of our hash function has a different keys data. So like, for example, okay, let's say, so ignore these numbers in pink. So basically, linear probing, in my own words, is, let's say you have a hash function that generates the first value. Okay, let's say we wanted to add in SpongeBob. Now, it evaluates to the index 0, so we put in SpongeBob. So SpongeBob is here, okay? Next, we want to add in Patrick. So let's say it evaluates to index 0 again. Now, if that happens, SpongeBob is taking up the 0th index, right? So this is full. And then let's say 1 has an X in it, it's full. 2 has an X in it, it's full. 3 is empty, so we place Patrick in 3. Basically, it's just going linearly until it finds an open spot. If the result is same for a key, if it's taking it up, then it just keeps going down the array and it puts it into the first empty slot. A common method is called probing. Probing means to continue to find the new array indices in a fixed sequence until an empty index is found. So that's basically what probing is. And then suppose we want to associate famous horses with their owners. First, we want our first key to be Buse. I don't even know how to call it. We'll just call it B. And then to store our first value, Alexander the Great, our function returns an index 3, so we save Alexander the Great with our key B into the array at index 3. After that, we want to store Seabiscuit's owner, Charles Howard. Unfortunately, Seabiscuit also has a hash value of 3. Our probing methods add 1 to the hash value and tells us to continue to look at index 4. Since index 4 is open to store, so we store Charles Howard. So it basically moves from 3 to 4 like that, if it's there, right? So yep, that's basically it. That's basically linear probing. You just keep going. If there's a collision, you just keep going down until you find an open slot. So other open addressing techniques. So there are more sophisticated ways to find the next address after a hash collision, although anything too calculation intensive would negatively affect a table's performance. Linear probing systems, for instance, could jump by 5 steps instead of 1 step. In a quadratic probing, quadratic probing open addressing system, we add increasingly large numbers to the hash code. At first, we just add 1, but if the hash function collides there too, we add 4, and the third time we add 9 because it's quadratic, right? So it would be 1 squared, 2 squared is 4, and then 3 squared is 9. So having a probe sequence change over time like this avoids clustering. Clustering is what happens when a single hash collision causes additional hash collisions. So imagine a hash collision triggers a linear probing sequence to assign a value to the next hash bucket over any key that would hash to this next bucket would now collide with the key that, in the sense that don't belong to the bucket anyways. So it just keep on going, right? Like if you had like 10 elements and they all collided, you would need to keep probing to the next one, to the next one, to the next one, and it kind of just drains it, right? So that's why clustering is bad. We don't want all the keys to be in the same spot. So as a result, new keys need to be assigned to the next bucket over. This propagates the problem because now there are two hash buckets taken up by key value pairs that were assigned as a result of a hash collision. All right, so we're gonna just review hash maps real quick. So a hash map is built on top of an array using special indexing system. It's a key and value storage with fast assignments and lookup. A table that represents a map from a set of keys to a set of values. And again, it's a dictionary in Python, basically. Hash maps accomplish all this by using a hash function, which turns a key into an index into the underlying array. A hash collision is when a hash function returns the same index for two different keys. Now, there are different hash collision strategies. Two important ones are separate chaining, um, where each array index points to a different data structure, and open addressing, where a collision triggers a probing sequence to find where to store the value for a given key. So that is going to be hash maps in a nutshell. Next, let's go ahead and take the quiz for hash maps. It's very short here. So given a hash table that handles collisions, which of the following would need to be saved so the values can be assigned, reassigned, and looked up? So given a hash table that handles collisions, which of the following need to be saved so that the values can be assigned, reassigned, and looked up? So probably the key, definitely the key and the array. I'm thinking the hash code. Do you think the hash code and the value? I think it is the hash code. Probably the hash code. Or you think it's the array index? I would think it's the array index and the value. Oh, it's a key in the value, okay. Well, you need the array index to find the v. This doesn't help when we're looking for the key and when we're looking for the value and only know the key. Okay, so it's the key and the value. Okay, makes sense. So what does the collision strategy called open addressing when it finds a collision? Ignores the assignment and waits for the next method call, adds the value to an underlying linked list, looks for another cell. Yep, it keeps going until, so like linear, quadratic. Yeah, that's open addressing. How does a hash map turn the hash code for something into an array index? By dividing the hash code into 4 different possibilities and choosing the one that's empty, using the modulus operator via a compression method, or a hash map picks the next available space in an underlying array. So how does a hash map turn the hash code for something into an array index? I think it's a hash function, right? It uses a compression method like that. Which of the following is true about a hash function? It can't accept integers as inputs. It is not reversible. Two different inputs can never have the same output. It performs a complicated numerical calculation. Two different inputs can never have the same output. Good question. I'm actually not sure. I think it's D. It's not reversible. Hash functions need not calculate much, so as long as a single key always gets the same hash value. Okay. Let me go ahead and retake this quiz. Again, it's going to be key in value. Looks for another cell. Yep, that's open addressing. And then hash map turns the hash code using the modulus operator, and then it is not, hash functions are not reversible. Yeah, hash functions compress data, so an input cannot be retrieved from its own output. Okay, makes sense. So that is gonna do it for hash maps. Thank you so much for watching, and again, top link in the description if you want to learn more about how to get a job or an internship in tech. But with that being said, if you enjoyed this, please like and subscribe, and I'll see you in the next one.